Dark matter, a component of the universe whose presence is discerned from its gravitational attraction rather than its luminosity. Dark matter makes up 30.1% of the matter-energy composition of the universe. The rest is dark energy, 69.4%, and ordinary visible matter, 0.5%. Originally known as the missing mass, dark matter's existence was first inferred by Swiss-American astronomer Fritz Zwicky, who in 1933 discovered that the mass of all the stars in the Coma cluster of galaxies provided only about 1% of the mass needed to keep the galaxies from escaping the cluster's gravitational pull. The reality of this missing mass remained in question for decades, until the 1970s, when American astronomers Vera Rubin and W. Kent Ford confirmed its existence by the observation of a similar phenomenon. The mass of the stars visible within a typical galaxy is only about 10% of that required to keep those stars orbiting the galaxy's center. In general, the speed with which stars orbit the center of their galaxy is independent of their separation from the center. Indeed, orbital velocity is either constant or increases slightly with distance rather than dropping off as expected. To account for this, the mass of the galaxy within the orbit of the stars must increase linearly with the distance of the stars from the galaxy's center. However, no light is seen from this inner mass, hence the name dark matter. Since the confirmation of dark matter's existence, a preponderance of dark matter in galaxies and clusters of galaxies has been discerned through the phenomenon of gravitational lensing, matter acting as a lens by bending space and distorting the passage of background light. The presence of this missing matter in the centers of galaxies and clusters of galaxies has also been inferred from the motion and heat of gas that gives rise to observed X-rays. For example, the Chandra X-ray Observatory has observed in the Bullet Cluster, which consists of two merging galaxy clusters, that the hot gas, ordinary visible matter, is slowed by the drag effect of one cluster passing through the other. The mass of the clusters, however, is not affected, indicating that most of the mass consists of dark matter. Matter is 30.6% of the universe's matter-energy composition. Only 0.5% is in the mass of stars, and 0.03% of that matter is in the form of elements heavier than hydrogen. The rest is dark matter. Two varieties of dark matter have been found to exist. The first variety is about 4.5% of the universe and is made of the familiar baryons, i.e., protons, neutrons, and atomic nuclei, which also make up the luminous stars and galaxies. Most of this baryonic dark matter is expected to exist in the form of gas in and between the galaxies. This baryonic or ordinary component of dark matter has been determined by measuring the abundance of elements heavier than hydrogen that were created in the first few minutes after the Big Bang occurred 13.8 billion years ago. The dark matter that comprises the other 26.1% of the universe's matter is in an unfamiliar, non-baryonic form. The rate at which galaxies and large structures composed of galaxies coalesced from density fluctuations in the early universe indicates that the non-baryonic dark matter is relatively cold, or non-relativizitic, meaning that the backbones of galaxies and clusters of galaxies are made of heavy, slow-moving particles. The absence of light from these particles also indicates that they are electromagnetically neutral. These properties give rise to the particle's common name, weakly interacting massive particles, WIMPs. The precise nature of these particles is not currently known, and they are not predicted by the standard model of particle physics. However, a number of possible extensions to the standard model, such as supersymmetric theories, predict hypothetical elementary particles, such as axions or neutralinos, that may be the undetected WIMPs. Extraordinary efforts are underway to detect and measure the properties of these unseen WIMPs, either by witnessing their impact in a laboratory detector or by observing their annihilations after they collide with each other. There is also some expectation that their presence and mass may be inferred from experiments at new particle accelerators, such as the Large Hadron Collider. As an alternative to dark matter, modifications to gravity have been proposed to explain the apparent presence of missing matter. These modifications suggest that the attractive force exerted by ordinary matter may be enhanced in conditions that occur only on galactic scales. However, most of the proposals are unsatisfactory on theoretical grounds, as they provide little or no explanation for the modification of gravity. These theories are also unable to explain the observations of dark matter physically separated from ordinary matter in the bullet cluster. This proves dark matter exists.